Swayam Prabha. Digital India. Educated India.
Hello everyone. In our last class, we saw case studies of building in warm and humid climate. Today, let us look at the passive strategies that have to be adopted in the hot and dry climate. So, if we look at the suggestions that come out of Mahoney's tables for a hot and dry climate, the tables suggest that the simple passive strategies in hot and dry include orienting the building along the north and south with long axis along east and west. The building must be protected from hot and cold winds. Double banked rooms with temporary provision for air movement must be made available. Medium-sized openings of 20% to 40% must be available, and heavy external and internal walls must be designed. Roofs must be heavy with a time lag of 8 hours. Space for outdoor sleeping could be provided, and protection from heavy rain may also be necessary in some of the months. Now, having seen how passive strategies are selected using Mahoney's table, let us see how passive strategies are selected for a hot dry climate like Jaipur using software climate consultant. So, first let us see how to make the indoors comfortable for the month of March for a hot dry place like Jaipur. So, left to itself, 322 hours or 43.3% of the time is comfortable in March, whereas sun shading of windows makes 228 hours out of 744 hours as comfortable. Using high thermal mass with nocturnal ventilative cooling or night flush will make 223 hours out of 744 hours to become comfortable. Using direct evaporative cooling can make 226 hours out of 744 hours to become comfortable, amounting for 30.4%. Whereas, two-stage evaporative cooling can further push 233 hours, amounting to 31.3%. Adaptive comfort ventilation can push 211 hours, amounting to 28.4% of the time to be comfortable, whereas fan forced ventilation can make 52 hours as comfortable, which is just 7%, whereas internal heat gain can also help for 184 hours. So, if you see in Jaipur, according to climate consultant, for the month of March, you do not need any active means and 100% of hours, that is 744 out of 744 hours become comfortable just with adapting passive strategies. So, there is no need for active strategy for the month of March for a hot dry place like Jaipur. Now, let us see what happens in the form of how this translates into design guidelines. On hot days, ceiling fans or indoor air motion can make it seem cooler by 2.8 degree centigrade. Thus, less air conditioning may be required. This can be used on hot days with closed windows. Traditional passive homes in hot, windy, dry climate use enclosed, well-shaded courtyards with a small fountain that provides wind-protected microclimate variation by bringing in moisture or humidification to the air that enters inside. Earth sheltering, occupied basement or earth tubes will reduce heat loads in very hot dry climates because the earth stays near average annual temperature. So, you can have the earth air tunnel as a way of making the indoors comfortable, or you can simply have berming of walls to make the indoors comfortable. Use light colored building materials and cool roofs with high emissivity to minimize conducted heat gain. So, use materials with high solar reflectance index for maximum emissivity to minimize the amount of heat that is absorbed by the roof, and also for reflectance and emittance, and you must check the data from the manufacturer. Humidify hot dry air before it enters the building from enclosed outdoor spaces with spray like fountains or misters which will add mist inside, or having wet pavements. So, have roads on which you spray water, or have cooling towers. Window overhangs must be designed appropriately for this latitude, or you can have operable awnings or sunshades that you can extend in summer, and this can reduce or eliminate air conditioning. In order to produce stack ventilation, even when wind speeds are low, maximize the vertical height between air inlet and outlet through open stairwells, double-storied height spaces, roofs, attics, mezzanine floors, etc. Flat roofs will work well in hot dry climate, especially if they are light in color. Now, what happens in the month of June? What strategies which are passive in nature can be adapted to maximize comfort hours, and how much is that maximized comfort hours just with the help of passive strategies? So, if you do not apply any passive strategies, the indoors will be uncomfortable all the time. Whereas, if you adopt sun shading of windows, then 257 hours become comfortable out of 720 hours, amounting to 35.7%. Direct evaporative cooling amounts to 16 hours becoming comfortable, which is about 2.2% of the month. Then two-stage evaporative cooling shifts the comfort hours by 65 hours, whereas adaptive comfort ventilation will give indoors 77 hours of comfortable time. With these strategies, 19.7% of the month of June, which is approximately 20%, will be comfortable. However, 80% of the time will be uncomfortable with just passive strategies. With passive strategies. Now, how to make 100% of the time comfortable? So, we have already seen that if you don't adapt any strategies, then nil. The whole month will be uncomfortable. Whereas solar shading will make 257 hours as comfortable. Direct evaporative cooling will make 16 hours as comfortable. Two-stage evaporative cooling will make 65 hours as comfortable. Adaptive comfort ventilation will make 77 hours as comfortable. However, it will not make 100% of the hours comfortable unless you use an air conditioner, and the air conditioner will make 578 hours, or the remaining 80% of the hours will become comfortable only if you use air conditioning, and that is how we can achieve 100% comfortable hours for the month of June for a hot dry climate like Jaipur. Now, what are the strategies that must be followed to make indoors comfortable for the month of June? So, on hot days, ceiling fans or indoor air motion can reduce indoor temperature, and that can reduce the load on air conditioning. Shaded outdoor buffer zones such as porch, patio, lanai oriented to the prevailing breezes can extend living and working areas in warm or humid weather. We can provide double pane high performance glazing, which is actually low E glazing, on west, north and east, but clear on south for maximum passive solar gain if needed, or we can use appropriate finishes for the glass so that you do not invite heat inside. To facilitate cross ventilation, we can locate door and window openings on opposite sides of buildings with large openings facing upwinds if possible. To produce stack ventilation, even when wind speeds are low, maximize vertical height between air inlet and air outlet through open stairwells, two-story spaces and roofs in the form of attics or mezzanines. Now, what are the strategies that can be followed for the month of September to make the indoors comfortable only with passive strategies? Left to itself, the hot dry climate of Jaipur for the month of September will have 6 hours comfortable without any intervention, whereas solar shading of windows will push 251 hours out of 72 hours to become comfortable. By using adaptive comfort ventilation, 351 hours out of 720 hours become comfortable. Thus, only 49% of the total month of September will be comfortable if we use passive strategy. But we want to make the remaining 51% also as comfortable. How do we do that? If we want to make the remaining hours also comfortable, then you will have to adapt active strategy. Passive strategy, such as not indulging in much intervention, solar shading of windows, adaptive thermal comfort, will cause shift in comfort hours by 6 hours, 251 hours and 351 hours respectively. Whereas for 100% comfort, we need to dehumidify the air, which will push 191 hours into comfort. Whereas using air conditioning will push the building into comfort mode by 307 hours, which is 42.6% of the month. Thus, we can get 100% comfortable hours for the month of September in a hot, dry place like Jaipur. So, how does this translate into design guidelines? So, for design guidelines, on hot days, the ceiling fan or indoor air motion can reduce the indoors by approximately 2.8%. Shaded outdoor buffer zones such as porch, patio, lanai oriented to the prevailing breezes can extend living and working areas in warm or humid weather. Good natural ventilation can reduce or eliminate air conditioning in warm weather if windows are well shaded and oriented to prevailing breezes. Using light colored building materials and cool roofs with high emissivity can be used to minimize conducted heat gain. Whereas, in order to facilitate cross ventilation, we must locate the door and window openings on opposite sides of the building with larger opening facing the windward side as far as possible. Window overhangs should be designed, or we can use operable sunshades that extend in summer and can reduce or eliminate air conditioning. To produce stack ventilation, even when wind speeds are low, maximize vertical height between air inlet and air outlet by having open stairwells, double height space or two-story space, and having appropriate roofing. So, these are the strategies for the month of September as suggested by climate consultant. Now, for the month of December, what are the passive strategies that we must use to have 100% as the comfortable hours? So, left to itself, 204 hours are comfortable without any intervention, whereas sun shading will make 87 hours as comfortable. Using direct evaporative cooling will push 24 hours out of 744 hours into comfort mode. Having adaptive comfort ventilation will push 155 hours out of 744 hours into comfortable zone. Internal heat gain can make 314 hours as comfortable, whereas passive solar direct gain with high mass can make 192 hours into comfortable. Thus, using only passive strategies only passive strategies, we can have 83% of the month of December as comfortable. However, if you want to make the remaining 17% also comfortable, then what should you do? Then you must go for active strategy, because 204 hours are comfortable without any intervention for December. 87% can become comfortable with appropriate solar shading. 24 hours can become comfortable with direct evaporative cooling. 155 hours can become comfortable with adaptive comfort ventilation. 314 hours can be comfortable with internal heat gain. 192 hours is comfortable with direct solar high mass walls, while having heating and humidification if necessary will push the remaining 123 hours also into comfort mode. Therefore, in order to make 100% comfortable, there will be intervention of 16.5% as an active strategy for December for a hot dry climate like Jaipur. Now, how does this translate into design guidelines? So, for December, for Jaipur, which falls under hot and dry climate, sunny wind protected outdoor spaces can extend living areas in cool weather like seasonal sunrooms, enclosed patios, courtyards or verandas. You must either be able to have designed overhangs, or you can have collapsible overhangs like awnings, and that can reduce the air conditioning load. For passive solar heating, you must face most of the glass areas south. This will maximize winter sun exposure. But for those windows, for these windows, you must also have adequate overhangs so that you don't end up overheating in summer. You should organize floor plan so winter sun penetrates into daytime use spaces with specific functions that coincides with solar orientation. Use a high mass interior surfaces such as slab floors, thick floors, high mass walls and a stone fireplace to store winter passive heat and night summer cooling. Heat gain can also occur from lamps, lights, various equipments like television, computers, rice heater and so on, and this greatly reduces heating needs that keeps the home tight, well insulated to lower balance point temperature of the heating equipment. If we look at comparative analysis of how we can strategize design for a hot dry climate like Jaipur, with just passive strategies, 100% of the month of March can become comfortable, while in June only 20% of the month is comfortable with passive strategy. 49% of September is comfortable with passive strategy, while 83% of December is comfortable with just passive strategies. The other strategies, passive strategies that we need to use in order to achieve these percentages are: sun shading of windows is applicable throughout the year, whereas for March, The strategies which lead to 100% comfort hours is high thermal mass with nocturnal air ventilation, direct evaporative cooling, two-stage evaporative cooling, adaptive comfort ventilation and fan forced ventilation cooling along with internal heat gain for few hours. Whereas in June, you require direct evaporative cooling just like how it was required in March. Whereas you do not require direct evaporative cooling, you require that only in the month of December. Two-stage evaporative cooling is required in June just like it is required in March, whereas adaptive comfort ventilation is required throughout the year March, June, September as well as December you require adaptive comfort ventilation. Internal heat gain is required for March and December, while passive solar direct gain from high mass is required in December. In order to meet 100% of the hours as comfortable, for the month of March, no active strategy is needed, whereas for June, cooling and dehumidification is needed. In September, cooling and dehumidification is required, whereas only dehumidification will also push many hours into comfort. For the month of December, heating and humidification is needed. Thus, for a climate like Jaipur, there are some months where you don't need any intervention in terms of using active energy, whereas for some months you require active energy along with passive strategies. Whereas in some months just passive strategy is enough to push all the hours of the month into comfort zone. So, we will see these applications now. Let us look at the detailed passive strategies for hot and dry climate. First is the building orientation and form. Now, the form and orientation constitutes two of the most important passive design strategies for reducing energy consumption and improving the thermal comfort for occupants of a building. It affects the amount of sun falling on surfaces, daylighting and direction of winds. Properly oriented building maximizes the amount of solar radiation in winter and minimizes the amount in summer. In predominantly hot regions, buildings should be ideally oriented to minimize solar gains. The reverse is applicable for colder regions. The longer walls of the building should face the north and south and avoid west orientation. Second is ventilation and openings. There isn't much to discuss about ventilation and openings because the size of the windows must be kept minimum or very small, as this can increase heat if it is kept bigger. The third technique is to have an earth-air tunnel. The principle of the earth-air tunnel is it is a technique that is used to generate cool air in the summer and hot air in the winter. The process involves moving the outside air through a duct system that is installed deep inside the Earth's surface. Because of the Earth's constant temperature throughout the year, it exchanges heat while passing through the ductwork. The working of the earth-air tunnel is a wind tower or a wind catcher is installed outside the main building in the direction of the flow of air around the area. It is then connected to an underground duct or tunnel to force the air to move in the direction of the main building. The depth of the tunnel should be more than 2 meters or between 3 meters and 4 meters. The optimal ground temperature required for conditioning the air is 3 meters below the ground. At any other depth, the temperature is not of the optimum value. Through the duct, it reaches an area where it is treated for temperature, humidity, and to remove dust particles. From here, it reaches inside the building and the air is circulated throughout the building. Fourth is earth sheltering or earth berming. A building can be called earth sheltered when it has a thermally significant amount of soil or substrate in contact with its external envelope, that is, having earth against its wall, on its roof, or being underground. There is underground earth shelter. Its working principle is that as we go about 4 meters below the earth's surface, the ground temperature is stable and almost equal to the average annual temperature of that place. Annualized geothermal solar or AGS uses a separate solar collector to capture the heat. The collected heat is delivered to a storage device which is soil, gravel bed or water tank, either passively by the convection of the heat transfer medium, that is air or water, or actively by pumping it. This method is usually implemented with a capacity designed for 6 months of heating. In the passive annual heating storage, PAHS, solar heat is directly captured by the structured spaces through the windows and other surfaces in summer and then passively transferred by conduction through its floors, walls and sometimes even roof into adjoining thermally buffered soil. It is then passively returned by conduction and radiation to those spaces which are cooler in winter. Fifth is evaporative cooling. Now, the principle of evaporative cooling is that it is a passive cooling technique that uses the natural process of evaporation, mainly of water bodies, to cool the air inside the building. This effect lowers the indoor air temperature and provides a cool ambient temperature inside. It is effective in hot and dry climate where humidity is very low. This system is mostly used in Indian desert areas and works as a desert cooler for them. The design recommendation includes having pools, ponds and water features immediately outside windows or in courtyards that can pre-cool air entering the house. As water evaporates, it draws large amount of heat from the surrounding air. In public buildings, pools and fountains can be used as a cooling element along with cross-ventilating arrangement of openings. Cooling tower may be used to evaporate pre-cool ventilation air for one or more air handling units, reducing the load on the mechanical cooling system. Use of porous materials. Roof materials can cause evaporative cooling effect. That is, the siliceous shale is able to reduce the roof surface temperature by about 8.63 degrees centigrade as compared to a regular RCC mortar roof. Air is in direct contact with the cooling media, which is water. Indirect evaporative cooling. In direct evaporative cooling, the most commonly used methods are water bodies and water sprays. Sixth is use of thermal mass. Thermal mass is the ability of a material to absorb, store and release heat. Thermal lag is the rate at which a material releases stored heat. The higher the thermal mass, the longer the thermal lag. High thermal mass materials like heavyweight construction materials such as concrete, brick and stone can be used. Low thermal materials comprises of typically lightweight construction materials like timber frames, and this is not advisable. In hot and dry climate, high thermal mass can help to passively heat and cool the home at a low cost. Thermal mass, or the ability to store heat, is also known as volumetric heat capacity. Volumetric heat capacity is calculated by multiplying the specific heat capacity by the density of the material. Specific heat capacity is the amount of energy required to raise the temperature of 1 kilogram of a material by 1 degree centigrade. Density is the weight per unit volume of the material, that is, how much a cubic meter of material weighs. The higher the VHC, the higher the thermal mass. When it comes to design recommendation, it is recommended to use thermal mass in climate with high diurnal temperature variation. As a rule of thumb, diurnal ranges of less than 6 degrees centigrade are insufficient. 7 to 10 degrees centigrade can be useful depending on climate. High mass construction is desirable for a diurnal range of over 10 degrees centigrade. Moderate mass is best for 6 to 10 degrees centigrade diurnal range. Mass levels should vary according to solar axis such as glazing type, orientation, area and shading. The appropriate mass color with low reflectivity like dark, matte or textured surfaces. Next cooling strategy we see is blinds and jalis. Jalis are perforated screens used as shading devices in buildings to reduce the heat gain and promote passive cooling. These block direct sunlight from entering the building while allowing for the circulation of fresh air. Blinds are used on glass doors, windows, openings to reduce the amount of heat directly entering the building. These are made with different materials like wood, bamboo, fabric, etc. and can be adjusted to control the amount of heat and light entering them. Jalis are typically made of wood, stone or metal and are designed to provide shade and ventilation while still allowing for privacy and air movement. The perforations of the screens allows for better circulation of air, which can help to reduce the temperature inside the building. The next cooling element is vegetation. Plants can be effective passive cooling strategy for building as they can help lower heat gain, block direct sunlight, improve air quality, enhance visual comfort and provide natural ventilation. Using ventilation as a strategy can be low cost and low energy shade providers. Their working principle is that it reduces direct sun from striking and heating up building surfaces and lowers the outside air temperature. This in turn affects the heat transfer from outside to building envelope and interior. The benefits of having vegetation in a building is it shades the building and the open spaces around it. Roof gardens or green roofs can be one of the elements where we use vegetation in a building. Shading of vertical and horizontal surfaces through green walls is another method. This vegetation helps in changing or redirecting the direction of the wind. They create buffer zones against cold and hot winds. When we use vegetation, it is recommended to use existing terrain of the site and natural topography. Use of local species for vegetation which are accustomed to the variation in temperature, rainfall patterns, soil, etc. for that region makes the vegetation less maintenance free. We must select low maintenance vegetation in terms of water usage and that which are resistant against local pests. Also, reduced lawn area in the garden is better in order to reduce the amount of water that is needed for irrigation. The next strategy is use of vegetation in various areas. When vegetation is used along pavements, reduce the area of hard paved surfaces through the use of grass pavers. Absence of hard surfaces also ensures lower ambient temperature. More pleasant for pedestrians to walk on a green soft surface that does not radiate heat. Deciduous vegetation can be used where it can be considered as a flexible shading device. During winter, the vegetation will shed leaves and allow the penetration of sunlight to the same occupied space which it would shade in the summer. Next is green roof, which is also a variation of vegetation. So, green roofs are roofs that are partially or completely covered with vegetation. It helps in reducing the amount of heat absorbed by the roof, reflecting sunlight and providing extra thermal insulation. The roof lowers the temperature of the building through the process of evapotranspiration. The design consideration includes, while designing the structure, green roofs have several layers that add some extra load to the roof. A soil depth of 300 millimeters is enough for the green cover. When it comes to waterproofing layer, extremely expensive to repair the waterproofing layer after installation. Adobe. Now let us look at some building materials that can be ideal in hot, dry climates. Considering that we studied that high mass is ideal for hot and dry climate. First is adobe. Adobe is a natural building material that is made from sun-dried clay brick with the addition of sand, silt and straw. This type of brick has a high thermal mass and can be used to store and absorb heat during day and release at night. Second is stone. Stone has a high thermal mass and can be used to absorb heat. Third is rammed earth. Rammed earth is a building material made up of soil that is compacted into forms. It has a high thermal mass and can be used to absorb and store heat. Fourth is terracotta tiles. These are also made with clay that is fired at a high temperature, which provides a high thermal mass and works the same as adobe bricks. If we need to look at the design consideration, then usually locally available natural sources as building materials is best to go. Also go with materials that have high thermal mass and natural cooling properties. Select materials that are lighter in weight and color. The next strategy that we will study about is the cool roof. A cool roof is designed to reflect more sunlight and absorb less heat. It is made up of highly reflective materials such as white or light colored coatings that help to reflect the sun's rays into the atmosphere. It uses solar reflective surfaces that maintain the lower floor temperature. Cool roofs reduce the temperature by 7 to 10 degrees centigrade. Materials that can be used for cool roofs include wood shingles, polymer shingles, clay tiles, concrete tiles, slate tiles, metal shingles, special coating, and special thermal proof sheets. Well, the next strategy that we will look at is the radiant cooling system. The radiant systems are installed in combination of large thermal mass to facilitate absorption and radiation. They are also used for optimizing performance of the systems, and these coils should be installed in floors or in ceilings. For heating purpose it is used, and it is used in ceilings for all the cooling purposes. Radiant floor cooling and heating has a system of pipes which runs across the roof in such a way that when the building needs to be cooled, cool water is pumped into the or cool water is sent into the tube, and through the process of conduction and radiation, it radiates the chillness into the room or absorbs the heat and makes the indoors cooler. When the indoors have to become warm, the water that is pumped inside must be warm water. Then next is night flushing. So night flushing works by opening up pathways for wind ventilation and stack ventilation throughout the night to cool down the thermal mass in a building by convection. Night flushing is most effective in climate with large diurnal temperature difference. The building acts as a sink throughout the day. The cool mass absorbs heat from the occupants and other internal loads. At night, when the building is not occupied, the outside air is cooler. The envelope is opened, allowing cooler air to pass through the building so that the stored heat can be dissipated by convection. Night ventilation in winter should be avoided. Temperature swing and time lag of the thermal mass of the material are the key factors to be included in the quantification of nighttime temperature. Next strategy is the wind tower. The wind tower, also known as wind catcher or badgir, is a traditional cooling architectural element that has been used in countries which are severely hot. They have two main characteristics. The first function is to catch the prevailing wind and direct it down to the interior spaces of the buildings. The second function is to extract the stale and polluted air outside, thus supplying clean ventilation. The limitation is during the winter, the traditional badgir still allows cold air into the building and shifts the warm air out. The effect of the tower depends upon the height of the wind catcher, which is directly proportional to the wind speed, the cross section area of the wind catcher shaft, which is directly proportional to the amount of air introduced inside the building, air inlet and outlet opening, it affects the speed. Entry opening should be perpendicular to the wind direction. The outlet opening should be near the ground. Minimum number of outlet openings should be present. Glazing is assumed to be clear and single glazing and covers about 14% window to wall ratio. The construction of the walls is single uninsulated leaf wall with concrete block wall. Traditional wind catchers in hot dry climates were built either of mud brick or more frequently of baked brick covered with mud plaster. They can be combined with earth cooling or evaporative cooling techniques for more effect. And one of the last strategies we will see today is the roof pond. The roof pond system is a passive technique that uses water stored in a pond located on the roof of a building to lower the indoor temperature through the process of evaporation. It is based on the property of higher heat capacity in water. Roof ponds can be inexpensive, enclosing water in plastic bags, metal or fiberglass tanks with rigid transparent plastic covers. They could have a pond liner, which prevents water seepage and ensures the integrity of the roof structure. Inlet and outlet vents are also present, openings strategically placed to allow air circulation and the exchange of cooled air with the building's interior. This technique can be adapted easily for heating and cooling as required. It is also cost efficient. However, it must be designed well to avoid seepage as well as leaks. So, with this, we stop today's class where we have seen the strategies that must be followed or the simple and advanced passive strategies that can be used in a hot and dry climate. We stop our class here and continue our next class with case studies of buildings with hot and dry climate. Thank you.